This is part 2 of 9.3, Polar Coordinates and Graphs. And we're going to start by looking at sketches of polar curves and connecting them to Cartesian graphs. So the first thing we're going to consider is y equals 1 minus 2 sine x, and we're only going to look between 0 and 2 pi for x. And we're going to see its relationship to the polar graph r equals 1 minus 2 sine theta. Since there will be unique y values on this domain, we can use a table to help us with graphing the polar graph. So what we're going to do is actually transfer these values onto our polar graph and create our inner loop limacin that we have for this polar equation. So they'll correspond directly into our theta points for that reason. So if you notice, we're looking at y comma x values and to graph onto our polar curve. So because x is going to be the angle and y is the value, and so in our polar graph we're going to have to switch their orientation. Okay, so here's the table of values, and one thing we want to take note is there is a section here of y values where we have negative values for a positive angle. And what that does is that's what creates the inner loop here. So we want to note that if we have a positive theta on a domain, the r is negative, what we're going to get is an inner loop. So we're going to see that this inner loop is created. Oh, sorry. In this region, we're going to be greater than pi over 6, but less than 5 pi over 6. And this is where the r values are negative. And theta is positive. Okay, so where are we going with this? So let's take a look at this problem here. To find the slope of the tangent line in a polar graph, polar coordinates, we can use the parametric form for dy dx from our previous lesson, along with the chain rule to establish a theorem. So slope of tangent lines in polar form are in this fashion. So if y equals f of theta, and it's a differentiable function, then the slope of the tangent line at some point r comma theta on the graph of r equals f of theta is this. So if you notice, we are still using our relationship dy d theta over dx d theta, which from the last lesson, that is how we find the derivative in parametric form. So we end up having to use the chain rule here. So we have f of theta cosine of theta, f prime of theta sine theta, and then the dx d theta will also have to use the chain rule. Now please remember that your dx d theta can't equal 0 at the specific point that we're looking at. Okay, so we can create functions x of theta and y of theta first, find their derivatives, and then divide. So you don't have to do everything in this big fraction at one time. You can go ahead and find the separate derivatives of dy d theta and dx d theta, and then simplify them into the fraction. Okay. So here's where we find our horizontal and vertical tangent lines. So we want where the slope is 0. So that means that the numerator, which is dy d theta, would have to equal 0. But please remember, if it can't be a horizontal tangent point if the denominator is also 0. It just has to be unique that the numerator is 0. And vice versa for the vertical tangent lines. So now we want dx d theta equal to 0, but not dy d theta. So the problem is, if they're both equal to 0, we're not going to be able to draw any conclusions at all. So let's do an example of this type of feature. So we're supposed to find the points at which this cardioid, given by r equals 1 plus cosine theta, has vertical or horizontal tangent lines. And then we're supposed to check it with a graphing calculator. Okay. So what we need is we need an x equation and a y equation. So we're going to get an x equation first. So our x equation is we're going to use r equals 1 plus cosine theta. And we're going to multiply by cosine theta in order to create x. So on this side, we're going to have r cosine theta, which will equal x, will equal cosine theta plus cosine squared theta. So we have x equals cosine theta plus cosine squared theta. And we're going to do the same thing for the y equation, except we're going to multiply by sine theta. So then we're going to have that r sine theta is going to equal sine theta plus sine theta cosine theta. We're substituting it in this equation. Okay, and of course that's going to equal y. Okay, next what we're going to do is we are going to find the derivatives. So x prime is going to equal minus sine theta minus 2 cosine theta sine theta, using our chain rule. Y prime is going to be cosine theta plus cosine squared theta minus minus sine squared theta. Because I first took the derivative of cosine, I'm doing product rule here, so I get a cosine squared, and then when I take the derivative of cosine, I'll get the minus sine, so I have minus sine squared. Now, a lot of times what you'll do is you will, if you can, it's easier to have your derivative in terms of one trig function. So I'll just change my sine squared into 1 minus cosine squared using the Pythagorean identity. And so when I simplify this, I get 2 cosine squared theta plus cosine theta minus 1. Okay, so now I can find my horizontal and vertical asymptotes. So I'm going to find y prime over x prime, and for my horizontal ones, I'm going to want the numerator to equal 0, which is y prime. So I'm just going to do them separately, and that's perfectly okay to do that. So for the horizontal asymptotes, I'm going to let y prime equal 0, and so that's going to equal 2 cosine squared theta plus cosine theta minus 1. And what I want to see is this is really a quadratic. So I'm going to treat theta like it's, or cosine theta like it's x. So I can think of this as 2x squared plus x minus 1, and use the quadratic formula. So what I'm going to get is I'm going to say that, let me do that in that color. So I'm going to say that cosine theta is going to equal, so negative b, which would be negative 1, because I have a 1 in front of the cosine theta, plus or minus the square root of 1 squared minus 4 times 2 times negative 1. And that's all going to be divided by 4, 2 times a, and a is 2. Okay, when I simplify this, I am going to get negative 1 plus or minus the square root of 9 over 4. So cosine of theta, cosine of theta is going to be either -1 or +1/2. So what angles have those trig values? So the angles I get here then are theta for -1 could be pi, and that's the only one. And then for 1/2, I'm going to have pi over 3 and -pi over 3. Okay, for that. Now, I'll do the vertical tangents over here. So for vertical, that means I'm going to let the denominator of dy dx equal 0. So that means x prime equals 0. So that's negative sine theta minus 2 cosine theta sine theta. So I can factor out a sine theta or a negative sine theta. So negative sine theta is going to equal 1 plus 2 cosine theta, and that equals 0. So that I can just ignore the negative sign. And so that's going to happen at, so I can say where sine theta equals 0 or cosine theta equals -1/2. So, so for this one, the sine, that is at pi and at 0. And if you notice here, I have a crossover, pi here and pi here. So I have no conclusion about that one. So that has to be out. And then I have 0. And then cosine of theta is -1/2 in the range we have here. And it is at 2 pi over 3 and 4 pi over 3. And if you wanted to write this one as 5 pi over 3, you could. So these are going to be our angles then. So the verticals are going to be at 0, 2 pi over 3, 4 pi over 3. And the horizontals are going to be at pi over 3 and 5 pi over 3 for that problem. Okay, moving on then. Tangent lines at the pole. So if f of alpha equals 0 and f prime of alpha is not equal to 0, then the line theta equals alpha is a tangent at the pole to the graph of R. So at the pole means it's tangent right at the center. So if you find the zeros of R equals f of theta, they can help you find tangent lines at the pole. So in this example, we're going to look at a 3-reliefed rose curve that has more than one tangent line at the pole. So here's our rose curve. R equals 4 sine 3 theta. So the first thing we need to do is find the derivative, because if we're talking about tangent lines, we need the derivative. So we'll start with that. So our derivative is going to be, and let me move this back down a little bit so I have my x and y equations. Let me just write this here. So if I multiply that by sine, that's going to be y. So that'll be 4 sine theta sine 3 theta. Now be careful you don't put those together, because one is theta and one is 3 theta. And if I multiply my rose curve by a cosine theta, that means that my x is going to be 4 cosine theta sine 3 theta. Okay, so now I can take my derivative. So dy dx is going to be, I'm going to have to use the product rule and chain rule because I have a 3 theta here for y prime. So I am going to get 4 cosine theta sine 3 theta, and then plus 12 sine theta cosine 3 theta. And then the denominator is going to be, I just have to use the product rule and the chain rule there as well. So I'm going to have, if I take the derivative of cosine, so I'll have negative 4 sine theta sine 3 theta, and then plus, now taking the derivative of sine 3 theta, that'll give me 12 cosine theta cosine 3 theta. And that's fine. You can just leave it right like that. Part B says, calculate the slopes of the three tangent lines for the curve at the pole So those occur at 0, pi over 3, and 2 pi over 3. And so what we're going to do is we're going to substitute those values into our derivative and find the values. So the first one we're going to do is we'll do dy dx at theta equal to 0. And I'm literally just going to substitute in my derivative from part A and just write the values down and simplify them. So I'm going to have 4 times cosine of 0, which is 1, sine of 0, which is 0, plus 12 times sine of 0, which is 0. So it doesn't matter what this is. This would be -1, but not that it matters. Well, you'd have 0, so it would be +1. And then the denominator will be, so the numerator is 0. So as long as the denominator isn't 0, the slope will be 0. So -4 times 0 times 0 plus, hopefully this is not 0, 12 times 1 times 1. So since its denominator is not 0, this is going to equal 0. Okay, so that would be a tangent line like this. So this is y prime equal to 0. Okay, next one, we're going to do dy dx when theta equals pi over 3. So same thing, substituting. We have 4 times cosine of pi over 3 is 1/2. Then that would be sine of pi, which is 0. And then plus 12 times sine of pi over 3, which is square root of 3 over 2, times cosine of 2 pi. I'm sorry, I'm doing pi over 3. So cosine of pi, which would be -1. That's going to be divided by -4 times sine of pi over 3, which is square root of 3 over 2, times sine of pi, which would be 0, plus, hopefully this is not 0, 12 times cosine of pi over 3, which is 1/2, and then we're going to have cosine of pi, which is -1. So when you simplify this, these terms can be ignored. So I have -6 square root of 3 in the numerator and -6 in the denominator. So I get square root of 3. So our tangent line here, so it's going to be tangent to that curve. This is y prime equal to square root of 3. Okay, and then the next one is going to be dy dx at theta equal to 2 pi over 3. And I'm not going to go through, you're going to do the same steps you did here, and you're going to get negative square root of 3, which would make sense because you're going to have this tangent line here. Whoops, I totally missed the curve, the pedal. So I still missed it. One more try. Whoops, I had my eraser on. I so apologize for that. So there's that one. And then that's a little better. It'll look like this. So that's part B. And then in part C, it says, use a graphing utility to find the location of all horizontal tangent lines. Discuss any significance of these points. So we do have the graph here of dy dx already for us. So if we want the horizontal tangent lines, what we want is where dy dx, actually dy d theta equals 0, just that part. And so that is equal to our derivative we found in part A, the numerator. So 4 cosine theta, 3 sine theta. Let me write that better. So we have 4 cosine theta, and then we have sine 3 theta, plus 12 sine theta, cosine 3 theta. And again, you're just going to put this in your graphing calculator and find where it equals 0. You're not going to have to do this algebraically. So if you put that in your calculator, you'll find that it happens at all the points. And the nice thing is the graphs here. If you were to put that in your graphing calculator, you'll get this, and then you can trace these points. And here you have 0.659. Here is pi over 2. Here is 2.482, and then of course we're here at pi again, and I forgot to mention 0. So there are 5 points. So theta is going to equal 0, a pi over 2, pi, and then the 2 decimal ones that I found, which is 0.659 and 2.482. So there are the horizontal tangent line points. And so discuss any significance. And what we're going to see is that if we look at this, we have a this point right here and this point right there. We have horizontal tangent lines. And what we're going to find is that they are, so 0, -4 on our graph is the absolute minimum. And you can see that when you look at the graph. So I'm going to go ahead and I'm going to go under y equals here. And I am going to change this to polar coordinates. And I'm going to put my rose curve in. And I'm going to look at the points that we found the zeros in. So going to y equals, I'm going to put in there 4 sine 3 theta. And I'm going to hit zoom 5, see what I get. Okay, so that's pretty good. So let me hit zoom 6 to reset the window, and then I'll hit zoom 5 to square it up a little bit. That's kind of small, but it works. All right, so what I want to do then is if I trace this, I'm going to trace it at theta values. So here are 0, it starts out. And then if I want to put pi in there, so I can put in pi and go there. And so I have a value of 0 again. And then if I put pi over 2, I'm there, and you can see that at x equals 0, I have -4, and that's the absolute minimum of the graph. So that was one of my zeros. So that happened at pi over 2, but it's actually 0, -4 in the xy plane. So then if I put the other 2 points in, I'm not going to have anything significant either. So if I trace 0.659, I'm there. So I'm not really at, I can't say for sure at this point, but that is definitely a maximum. And the same will be said for 2.482. It should be on the other one at the same point. So that's a maximum as well. But I can say for sure that 0, -4 is an absolute minimum. So that's why I put that for that point. And then finally, we have 2 more parts here and we're finished. So find the 3 points where the absolute value of r is a maximum. Show that the tangent line is perpendicular to the line segment connecting the point to the origin. So it is going to be a maximum. This is the important point here. The absolute value of r is a maximum when our sine value is a maximum. So that occurs where, because remember we have sine 3 theta, where that's either a +1 or a -1. Okay, so that means that 3 theta has to be either pi over 2, 3 pi over 2, and also 5 pi over 2 to get all of the loops of the curve. So if we divide out the 3 for each of those, that means this is going to happen at pi over 6, pi over 2, and 5 pi over 6. And you can see that on our picture as well. Okay, so now we want to show that the tangent line is perpendicular. So what we have to show is that we have negative reciprocals here for these points. So if I substitute in the derivative dy dx, if I substitute in my new theta as pi over 6, and I'm going to skip the work for that, I'm going to get negative square root of 3. And I'll just do that first for all three of these. And then the last one is dy dx at theta equal to 5 pi over 6. And that's going to equal square root of 3. So I have to show that they're perpendicular. So in other words, I want to show that, here's what I'm showing. I drew, here is the line through the rose petal. I want to show that those lines are perpendicular like that. Okay, that I'm making right angles there. And I do that by taking that the tangent of pi over 6 should be the negative reciprocal of this, which it is. Tangent of pi over 6 is square root of 3 over 3, which is the same as 1 over the square root of 3. So they're negative reciprocals. The tangent of pi over 2 is undefined, which would be the reciprocal of 0. That's the perpendicular to 0. And then finally, the tangent of 5 pi over 6 equals 1 over negative the square root of 3. So they're negative reciprocals as well. So it does show that. Okay, then finally, write an equation for the tangent line that passes through the point r theta is equal to 4 pi over 6. So what I need then is I need my x and y values. So x at 4 theta, remember x is our cosine theta, and that is equal to 4 times the cosine of pi over 6. So that is going to be 4 times square root of 3 over 2, which is 2 square root of 3. And the same thing for the y, that's r sine theta. And that's going to be 4 times sine of pi over 6. And that's going to be 4 times a half, which is 2. And so I already know the slope, my dy dx at theta equal to pi over 6 is going to be, we found that in the last part, is going to be negative square root of 3 so I can write my equation. So y is going to equal negative square root of 3 times x minus 2 times the square root of 3 plus 2. We'll be doing more practice in class tomorrow. So if you have any questions, wait till then.